Swayam Prabha. Digital India. Educated India.
Yes, sir. We are live on YouTube as well as on Zoom. So let us wait for the students to join.
Yeah. Would you like to send a reminder or something to them, or it's okay?
Not required, sir, because
Okay.
we posted an announcement 2-3 days back only, sir.
Fine.
And there is a email list also. We have sent a reminder through SMS, sir.
Okay, that's fine.
So, and close to 1,800 plus students enrolled for this course, and 158 students registered for the examination, sir. And the examination date is on 2nd of November.
Okay.
So, and then right now we are on the 12th week, sir.
Yeah, so I think the course is over now, I
Right,
believe.
sir. Except assignment solution, like assignment 12 solution, we will be releasing next week, sir. So with
Sure.
that one,
Yeah.
the course will be complete, sir.
So I also wanted to talk to them and give them some materials for
Right,
them to practice. So if they
sure.
join, it's fine. Otherwise, I'll upload them the materials on the portal.
Yes, sir.
So that they can access it from there and
Yes,
use
sir.
it for their simulation.
Yes, sir. After uploading, we will post an announcement saying that this has been uploaded, sir.
Sure. Okay.
Right, sir. So anything in general, if you want to discuss, you can discuss, sir. Because since it is getting recorded, students will watch it later also, sir.
Yeah. So
Yeah.
okay. So we have a student now.
Yeah. Mr. Siva Aditya. Can you unmute yourself?
Yes, sir. Good evening.
Yeah. So please go ahead. Professor Rajesh Ranjan sir is with us. You can ask doubts.
Yes, sir. So actually, the course was not actually how I really assumed it to be, because I was mainly expecting the course to be the like with much explanation regarding the softwares and stuff. But initially, it was very difficult to cope up, sir. All the differential equations and those,
Okay.
the math behind the actual CFT, it was very difficult. But as the weeks went on, it was very useful to understand how those were the basics which are implemented in. So I would like to thank you actually for creating a strong foundation in the principles. It was very useful.
Okay.
I just mainly came here to thank you and nothing much. I don't really have much of doubts. So
Okay.
yeah, yes, sir. But I would like to ask one question, sir. I'd like to pursue a career in CFT. So what do you think would be a good field of research in the upcoming generations in terms of CFT, sir?
See, nowadays CFD is there everywhere. Okay, whether you are in aerospace or mechanical or chemical engineering, material science. Okay, in every field, wherever you want to design something or want to modify some design, or want to optimize something, want to get some flow variables. Okay, so CFD is the first choice. So as we discussed in the very beginning of the classes, that earlier you used to experiment for everything, right? So right now, let's say if you have to go for like 20 stages to get a design, you would probably go to 10 stages using CFD, then do an experiment, then 10 stages using CFD, then do experiments, right? So it is cheaper. So in that way, what I suggest you is that, as you told that you need a very strong foundation in CFD, because using a software is not enough. I mean, of course, it's a good thing that you know the software, whether it's Fluent or OpenForm or any other software. But instead of using this as a black box, if you can understand what is going on behind, if something works, why it should work, or if something does not work, why it does not work, or before you even select a scheme or make a grade or basically decide what kind of models you want to use, you should have some fair idea that, okay, this is going to work. okay, or this is not going to work. For example, if the flow has got very high separation and you're using a K-epsilon model, it's not going to work. Okay, you may be wasting a lot of time, but it's not going to work. Right, so we discuss about why there are limitations in certain turbulence models, right? Similarly, let's say you want to capture a shock, right, and you are using a scheme which does not have that capability, or maybe you're using a pressure-based solver without using the energy scheme, right? So you are basically barking on a wrong tree, right? So you are basically not solving the problem which is expected. So the purpose of the course was to give you a foundation and an understanding that how you should basically think about CFD. Having said that, if you have a good foundation, I think there are plenty of opportunities and it's only going to increase in the future. What I also foresee in the future is that there will be an amalgamation between the AI and CFD. Okay, so basically, you see that we have been discussing that some of the models do not work, or you have to tune the parameters for it to work, right? So how AI can help, or the ML can help, machine learning can help, is basically it can give you the tuned parameters very easily rather than doing it manually, right? So that way you can tune the parameter, get the proper coefficient of a turbulence model, put it in a certain equations, and solve it, and you get the better solution. Right, so the future is going to be CFD plus data science and plus AI and ML. Okay, so all three are basically kind of related also. So when you do CFD, you get a lot of data, right? So how to analyze the data? Can you get a reduced order model from that? When I say reduced order model, that means that let's say you did some simulation at some Reynolds number, and you want to find out the value at different Reynolds number. Right. Instead of doing CFD, which can be very expensive, can you get a model which can learn from all these things at different Reynolds number and give you a value at the Reynolds number that you desire? Right. So it's a combination of all three which is going to dominate the market in the future, and it is going to be in every engineering field, even in physics also. So the three things that you should be strong at, and the foundation of everything is kind of good command on scientific coding. Okay, one is CFD, other is data science. Okay, and third is AIML. Okay, I hope I answered you. I mean, at least a bit.
Yes, sir.
Okay.
Yes, sir. Got it, sir. Sir, and is there any specific application of CFD which you think would be very much useful in aerospace industry, sir, for
Yeah,
research and
see,
development?
aerospace is particularly very, I mean, if you want to do any experiment, it's very expensive. Okay, the wind tunnel costs are very high. Okay, and it's not easy to, and in fact, in aerospace, let's say you want to launch a rocket, right? So to get the temperature and the pressure of the environment, it's not easy. I mean, if you want to put a probe to measure, the probe itself will melt. Right. So what scope you have is, I mean, you can do good high fidelity CFD, get the parameters, and based on that understanding and your experience, you can design something. So in aerospace, particularly due to two main reasons, one is that it's very expensive. It's an industry which is very different from, let's say, chemical or mechanical or many other such industries. And secondly, it works in an environment which can be hypersonic, where the heat transfer is very high. The flow can be transitional. Okay, where predictions is not very easy. Flow can be highly turbulent. All those features are there. So that way, aerospace. I mean, in aerospace, I think CFD is going to stay for a very long time.
Yes, sir. Thank you, sir. Understood.
Sure. Yeah, there is a question on chat. I think by Omkar. I want to pursue my future in CFD itself, but I do not have master's degree, so I don't have any opportunity in research area. Is there any alternative? No, I mean, I won't say that, I mean, there is no opportunity. There are a lot of opportunities depending on what level you want to get involved in. Okay, so if you want to do a CFD, first of all, right now you have done this course, you have a decent foundation. Okay, now the second thing is that you start solving problems. Okay, and get good experience in some or other software. Okay, and there are many opportunities in academia as well in research field as well as in the industry that you can apply and go there. You learn there, learn while you are working on the problem, and then you can go ahead from that, right? So it's not mandatory that you should have a master's degree, but of course, master's degree help, right? Because I mean, it's a kind of advanced course, CFD. I mean, people take it in third year and final year also, but it's a kind of advanced course. So if you have a master's degree, it helps. So there also you can try or plan for a master's degree. Yeah. So next question is Shravani. Are you ready? You have any question? Yeah. So there was a lot of noise. I closed the door.
Ms. Shravani, can you unmute yourself and ask doubt? Or else you can post it on the chat box also. Let's give her some time, sir.
Sure.
Right.
Okay. Omkar Sinde has followed up with a question. I'm working as a hydraulic engineer in an MNC company, but due to not having master's degree, I'm getting rejected by University of PhD for PhD and even for other company. See, PhD is a different ball game. If you want to go for PhD, it is expected that you have higher degree or maybe basically higher understanding. Of course, there are some universities which allow you, and but most of the universities allow you after the BTech, but it's highly competitive. If you have certain publications, and if you have a strong basically presence in that particular field, they may consider you for PhD. But if that is your query that you want to go for higher studies doing PhD, I would recommend go for masters. Okay, and then from there you can take over for PhD. Okay, and then I mean I cannot specifically answer this that CV getting rejected from other companies because that is company specific. But all I can say here is that you have a lot of scope if you want to do PhD, and if you are in this field, I'm sure I mean it's going to help you in the future also. Okay. There's a query from you too, sir, from Shreyans Kundu. Do you think with the rise of quantum computers, the chances of doing 3NS simulations will increase? It is very difficult to say as of now. I also work in quantum computing, okay, and we started doing some preliminary simulations, porting our code to quantum computers. But what we have felt till now is that the quantum computers is not like something it's going to affect every single field. Okay, it's good for certain field, for example, in crypto, okay, where it's very important to keep something hidden from the public. Okay, so I mean, in those fields, the quantum is very, very good. It's going to it's a kind of the future in those kind of fields. Okay, but in certain fields like CFD, we are yet to see the potential of quantum computing, which basically supersedes the performance of the classical computers that we have. Okay, for example, right now we don't have algorithms which can basically solve non-linear problems like problems with socks with a great accuracy in quantum computers. Right, so the algorithms are being developed now. Okay, but as of now, I cannot comment on this whether this quantum computers can really basically bypass classical computers in terms of simulation power.
Thank you, sir, for answering that query.
Yeah.
And one more student has joined, Mr. Kushal Singh. Mr. Kushal Singh, can you unmute yourself? It says connecting to audio.
Yeah. So generally, I think for everyone, before more people join, is that I just want to, I mean, understand that you followed this course and you're able to basically understand some basics of the CFD. So that was the purpose of this course. Of course, there are many courses, certificate courses in market, which can give you training on one or different software. Okay, but that was not the target. I mean, the target or the purpose of this particular course was that once you have the basics of CFD, you can use any software that you want. Okay, with some practice. Right. So I'm sure that after taking this course, and if you have done this course seriously, you go to any tool and you'll find it more easy to use than what used to be earlier, right? Whether it's Fluent or Star CC, Plum Plus, or maybe OpenFOAM or Console, or any other tool that you like. So we started from very basic equations. Okay, what are the equations that are being solved? We saw the compressible form, the incompressible form. Then we looked at many different ways of writing those equations. Then we non-dimensionalized those equations. Then we looked at simple schemes to solve 1D problems. Then we went to 2D problems. And then we went to the turbulence models. We actually spent around 2 weeks on turbulence models. Okay, then we talked about the LES if you want to perform LES, because LES, although it's expensive, more expensive than the rank simulation, much more expensive, but still because the computational powers are increasing, so I think people are doing more and more LES. So it's very important to have background in LES as well. Okay, and finally we talked about the boundary conditions, and at the end we had some case studies. So it was a kind of package which wanted to introduce the concepts of CFD to you, to everyone. Okay. There is a question from Shravani. I'm doing my final year project in NARL Airflow Lab, but I am having difficulties in MATLAB. Okay. So I think in the beginning we had shared some resources on MATLAB. You can probably go through those resources and hone up your skills in MATLAB. But having said that, I think this purpose of this course was not to give you a training in MATLAB. Of course, if you are good in MATLAB, you can write the codes easily, and you can appreciate the coding part in CFD more easily. But there are plenty of resources in MATLAB. And one thing that I want to tell to everyone is that I mean, whether it's MATLAB or any other coding language, it's all about practice. Okay, if you write, I mean, if you do a lot of practice, write many codes, you will get. I mean, it will seem to you easier day by day. Okay, so. So I hope that you can get accustomed to the MATLAB commands and tools and maybe use it more effectively for your research. We have Kusal and Athis. If you have any questions, please unmute and ask the question.
Good afternoon, sir.
Yeah,
This is
welcome.
Kushal Singh. I am doing PhD in Aerospace Engineering from UPS Dehradun. I am continuously following your lecture and doing all the exercises done by you. So I am in the 11th week of the lecture now. So I just wanted to ask, sir, like how do we know that whether our case is sensitive to turbulence intensity? And what will be its effect on lift and drag, basically at low angle of attack, near stall, and after angle of attack, or post stall?
So generally, I mean, if I can tell you broadly, I mean, it depends on flow to flow. But if I can tell you broadly, if the flow is in the regime where it is transitional, okay, so then it is very, very sensitive. Okay, so it can go either way. Okay, it can go a little bit of transitional, come back to laminar, or it can become turbulent. Okay, so then your behavior will be very, very different in these two regimes. Okay, so that's what happens, for example, in gas turbine blades. Okay, the Reynolds number falls very low as you go high in the altitude because the density is low there. Reynolds number comes around 20,000, 30,000. So now the flow is laminar, but there's a lot of curvature on your blade. So the flow may become transitional there because of the curvature. Okay. And in those cases, the effect of the intensity or even the length scale that you're using, those parameters are very, very strong. But generally, for example, let's say you want to simulate flow over a wing, okay, with a condition where it is fully turbulent, okay. So then if you are in the same ballpark figure, it will not matter too much. Okay, so for example, let's say you are talking about a wind tunnel, which is like 1% or 2% intensity. So even if you put 2.5% or 3%, it will not matter, right? So that's how it is. But some flows which are in the transitional regime where the flow can go either side, and you don't know that, or if there's a separation in the flow, okay, there is a strong interaction between the sock and the boundary layer. In those kind of questions, the problems, I think the intensity plays a major role. Okay.
Okay, thank you, sir. Sorry, I forget to mention the regime. That is, regime in which I am working is low subsonic, and the
Okay.
Reynolds number is 3 into 10 to the power 5.
Okay. So then it is likely to be sensitive. Okay. So you,
Okay.
because see, subsonic flows are more dangerous, okay, than the supersonic flow.
Yes, sir.
Okay, so we discussed also during the, I think, the boundary conditions also.
Yes, sir.
Okay, so the subsonic flow, because your flow can interact both ways. Okay, so my suggestion is that you have to do the analysis. Okay, do with different intensity. Let's say you are using 5% intensity. Then you also do for 10%. Okay, and see if the flow has changed greatly, the mean flow. Okay,
Okay.
of course, instantaneous flows will change, but if the mean flow do not change greatly, then it's not very sensitive. But if it is changing a great deal, then you can basically keep on doing something at 6%, 7%, and see how things are changing. Okay, but as I told you that it's very difficult to tell you without basically going through that process.
Yes, sir. I understand, sir.
Yeah. Okay.
Thank you so much, sir. It was good. Thank
Sure.
you, sir.
Okay. Yeah. Thanks. I hope the course was useful to you.
Yes, sir.
Yeah. So there is another question. What do you mean by first principle you referred to during the 10th week lectures? Okay, I don't recall exact context that you are asking, but generally the first principle is that which is basically derived from the first principle. For example, let's say you talk about the momentum equation or the energy equation or the continuity equations. Momentum equations, right? So all three conservation equations can be derived from the first principles, right? You know that the mass has to be conserved in the system, momentum has to be conserved in the system, energy has to be conserved in the system if you're not adding any heat or not dissipating. So those are the things which can be derived from the first principle, from the very, very basic law. Okay. For example, let's say you go to try to derive an equation for turbulent dissipation rate, epsilon or omega. Okay, so as we discussed when we're talking about the turbulence modeling, the range models, that it's an artifact. Like if you do an experiment, you never see the mean flow. Right? Let's say you run a wind tunnel and flow over a cylinder or flow over an aerofoil. You are never going to realize the mean flow. It's always instantaneous flow. It's after that you basically average it out, then you get the mean flow. Right? So that's a post factor. What we are doing in range simulation or the turbulence model simulation, that we start with the mean flow. We assume that what we are going to get is the mean flow. Right? So there is no instantaneous flow there. Right? So in order to get that, I mean, that is something we need to do to avoid the closure problem. You need to get additional equations which are not there. You have basically more variables than the equations. Then you have to cook up some equations. So we cook up equations like epsilon, the dissipation rate. But it cannot be derived. I mean, there is no principle that the dissipation should be basically generated like this or destroyed like this. So what we do, we follow the turbulence kinetic energy equation, the K equation. Okay, it will have some term which is time dependent, something on the advection, something on the dissipation, something on the transport. So basically follow the structure. Okay, but it has no principle that, okay, for example, Newton's law is kind of a, it's a first principle. You can get it from the first principle. So you cannot use any law to basically get that rate for the transport equation for the dissipation rate. So that's what I mean when I say the first principle. It's something which you can basically derive using the very basic, the fundamental laws of nature, or something that you are basically modeling. You are not using any fundamental laws, but you require it. So this is modeling it. So there is no principle behind it, but it is helping you. It's an engineering tool. Okay, it's not science, it's an engineering tool. You are basically approximating a system using some engineering approach. That's what I mean when I say it's not first principle. For the dissipation rate, for example. Kinetic energy, for example, we said it can be derived from the first principle. Right? If you want to derive a kinetic energy transport equation, take the momentum equations, multiply by U, V, and W, the three equations, add all of them. You will have del U square by del T, del V square by del T, del W square by del T, or add all three. You will have equation for del K by del T. So you have basically use the momentum conservation law and derive from there. But for the dissipation rate or the specific dissipation rate K or omega, or even the Reynolds number RE330 or maybe the gamma, there is no such first principle to derive those equations, the transport equations. Okay. Atish, you have any question? You can unmute and ask, or you can put in a chat box. Murli, any question on YouTube?
I just checked, sir. One student is watching on YouTube, and
Okay.
I will just send a reminder, sir.
Okay, fine.
Sir. So we got the following query from Mr. Sharad Kumar. What is the best technique to optimize a wind
Okay, vehicular assist
device geometry?
geometry. Okay, it's a very, very specific question. Okay, so if you are asking in terms of CFD approach, okay, so I don't know which device you have in mind. So you are talking about some ventricular assist device. So basically, you start with some data that you have from, let's say, from the hospital, with some geometry or some device that you have in mind. Okay, do the simulation and see if it is giving you the performance that you want. Okay, you might have to do it in a non-Newtonian way, because you might be thinking about the blood here. Okay, so so the blood flow is non-Newtonian. You have to basically model it. We have not covered that in the class, but I'm just telling you that the constitutive relation will be different. So you model that flow in that particular device, see if you're getting the desired performance. If not, you see where is the maximum stress, okay, where there is a chance of more rupture, or where there is the flow which is basically being not flowing properly or as you want. Okay, so then you modify the geometry, do the simulation again. But and you can keep on doing that till you get the performance. But ultimately, you have to go back and see it in a practical application, that what you are seeing in CFD is what you're getting here also not. Okay, so CFD is getting into the biology field, and of course, in biology, you have to be very, very careful because, first of all, like we said, that the flow is not Newtonian. Secondly, the boundary conditions are not known very well. Okay, so unlike the experiments or in the engineering flows where you have the boundary conditions well defined, here the boundary conditions are not that well defined. You have 1D model, lump size model kind of things are there. Okay, but they are not very well defined. So you have to basically ensure that what you're seeing in CFD is being followed in actual device also. Okay, when you design it and put it somewhere. Okay, so that's how you do it.
Thanks, sir, for answering that query. And on Zoom, students have left, sir.
Okay,
On YouTube, two are watching, sir. So let's wait for a few more minutes. In
sure,
case if there are no queries, then in that case we can wind up, sir.
sure,
Right, sir. And then before closing, you can give some tips for exam preparation, sir.
sure. I'll do
Our
that.
exam is on 2nd of November, sir.
Okay,
Right, sir. Thank
I'll
you,
do
sir.
that. What is the biggest error in CFD? Okay, so one of the, I mean, there are many errors in CFD. Okay, if you are not doing well, but the first thing that you need to be very, very sure that what kind of flow you are analyzing. Okay, whether it's a steady flow, unsteady flow, okay, whether it's incompressible flow, compressible flow, If it is compressible, it is subsonic flow, supersonic flow, hypersonic flow. Okay, whether it's Newtonian flow, non-Newtonian flow. Okay, so based on that flow, you have to select your uh, model and schemes and equations. Okay, if you fail to basically identify the flow, whether the flow has got separation, the flow is laminar, flow is turbulent, flow is transitional, okay, flow has got a relaminarization, okay, all kind of things are possible. Okay, so first of all, you should have a good idea about the flow that you're going to simulate. Okay, so based on, let's say, Reynolds number or Mach number or any non-dimensional parameter, you will have a fair idea. Or from the literature, you will find out, okay, in this Reynolds number, the flow is likely to be turbulent or transitional or laminar. Okay, subsonic, supersonic, all those kind of things. Right. So the biggest error will happen when, let's say, the flow was it's supposed to be compressible, and you put in assume that incompressible flow. Then it's going to be give you completely wrong result. Okay. Secondly, the boundary conditions. Okay, let's say you have everything fine, you have selected your equations properly, models properly, okay, schemes properly, but the boundary condition is wrong. Most of the students struggle in boundary conditions. Okay, what to put in the inlet and what to put at the outlet. Okay, so if the boundary condition is wrong, everything is going to be inaccurate. Okay, so the boundary condition errors are the most severe one, provided you have a good understanding of the flow. So that's what I would say. There are some errors in the schemes itself, for example, discretization error and dissipation error, but that is well documented in the literature. If you're using a scheme, you know what kind of errors that are expecting. So that you cannot basically cure. I mean, what you can do is you can use the best scheme that you have. Okay, but that is something that's not in your control. I mean, if you are developing a code, of course, there are people working in the schemes also to how to make a scheme better. Okay. Sometimes you can go to an approach which has got like very high order approach. It may be very, very computationally expensive, but then you can try that. Okay. So, yeah, so that's what I would say that, I mean, you need to basically take a full picture when you're doing CFD analysis.
Thank you, sir, for answering that query posted by Mr. Sharad Kumar. Right now, one student is watching, sir. Maybe we will give 2 minutes time.
Sure.
If we post, then we will continue, sir. So we are not getting any questions.
Okay, so maybe we can conclude then.
Right,
Okay,
sir.
so yes, students, if you are watching this, so I think you already know that you have your final exams on 2nd of November. Right, so I hope that you have taken all the classes seriously, submitted the assignments, and I mean, you must be knowing which part of the course you are not very good or very comfortable, and which part of the course you are very good. So I would suggest that take the course as a whole and revise basically all the assignments and all the concepts that you have learned during the course. Okay, so the question will not be very tough, but then at the same time, it will require you to have a good understanding about the fundamental aspects of CFD. Okay, so if you have taken the course seriously and if you have followed all the assignments and all the lectures properly, it's not very difficult for you. Okay, so I would request once again that if you have any notes or if you have any if you have prepared any notes from the course, please go through them. Okay, watch the important part of the lectures where you think that you were not very comfortable there or did not understand it clearly. You can ask the questions on the forum. Okay, but take this exam seriously. As I spoke in the last lecture that I'll be uploading some of the materials related to the safety simulation. So that will be available under the VIP web. So I thought I'll discuss with you and then upload that, but I'll upload it anyway, maybe in a couple of days, and that should be available for you. So those who want to basically start a career in safety and have no experience in doing safety simulations earlier may find these resources useful. Okay, so I wish you all a very successful career. Okay, and I hope this course was useful to you. Uh, I wish you all the best for your upcoming exam. Thank you very much.
Thank you so much, sir, for your valuable time. Participants, we are closing this session. Thank you, sir. Let's close it.
Thank
Yes.
you.
Yes, thank you.